We left off last time with a discussion of combinations and permutations and how we can use combinations in particular to figure out some simple probabilities. And now we're going to move on to some more interesting, somewhat tricky probabilities. We're going to start this discussion by looking at some data from the Titanic, just looking at data on adult male passengers. This data layout is referred to as a two-way table. We have two variables, what class the passengers were in and their mortality, whether or not they died or survived. and we have these row totals over here in the margin of the table, and we have some column totals down here in the margin of the table and a grand total here. These two numbers here should add up to 795, and these three numbers here should add up to 795. So a marginal distribution or a marginal probability is the probability of just a single event. So for example, you could say, if we weren't even talking about probability, you could say the marginal distribution of class is 176 in first class, 167 in second class, and 452 in third class. Or you could divide all those numbers by the grand total to get more of a relative frequency or a proportion or a percentage. 22% of the passengers are first class, 21% second class, 57% third class. And you could also do marginal distribution of mortality, the variable mortality. We have 664 who died and 131 who survived, or dividing those by the grand total of 795, you have 83.5% that died and 16.5% that survived. And so this can be a probability in the sense that if you were to pick one of these passengers at random, there's a 16.5% chance that the person survived. There's a 21% chance that the person was in second class, and so on. So we can also look at the distribution of each variable for a given value of the other variable. And this is often used to see if there's a relationship between the two variables. Remember, the two variables here are the passenger's class and the passenger's mortality. The mortality has two values, died and survived, and the passenger's class has three possible values, first class, second class, and third class. So you could look at the distribution of class just among those who died. And let me split screen real quick so we can see the table at the same time that we're seeing these numbers. So the conditional distribution of class among those who died. So just looking at this column here of people who died, you've got 118 out of those 664 who died that were in first class. So among those who died, 18% were in first class, 23% were in second class, and 59% were in third class. And you can also look at the conditional distribution of class among those who survived. 44% of those who survived were in first class, 9 or 10% of those who survived were in second class, 45 or 46% of those who survived were in third class. Because this distribution of what class people are in is different when you look at those who died compared to those who survived. That's the first step of seeing that there's a relationship between whether or not somebody survives and what class they're in. Or we should say a relationship between the variable class and the variable mortality. This is called a conditional probability, and it's usually written with this notation here, which is read A given B, or the probability of A given B, or the probability that A happens given that B has happened, or even a little bit more old school speak, the probability that A happens conditioned on B happening. So you would say the probability that someone's in first class given that they survived, is 44%. And that's this 44% right here. So we could also look at the conditional probabilities or the conditional distributions the other way. If we look at just those who were in first class, of those who were in first class, 67% died and 33% survived. Of those who were in second class, 92% died and 8% survived. Of those who were in third class, 87% survived and 87% died and 13% survived. So again, the distribution of mortality is different for each of the three classes, suggesting that there's a relationship between mortality and class. So those are also conditional distributions, and these decimal numbers are also conditional probabilities. The probability that someone survived, given that they're in third class, is 13%, while the probability that someone survived, given that they're in first class, is 33%. So, interesting that when you change the location of these two events on either side of this vertical bar, which kind of takes the place of the word given, it changes the probability. So the probability that someone survives, given that they're in first class, where are we at here? The probability that someone, I gotta scroll down a little bit farther, the probability that someone survived, given that they're in first class, is 33%, but the probability that someone was in first class, given that they survived, is 44%. So those two probabilities are not the same. Switching the order of the events in a conditional probability makes a difference. So that kind of leads us into a discussion of independence. So a lot of times when the question of independence comes up on a test, somebody will answer it in more colloquial terms, like they'll say, oh yeah, whether or not you survive is independent of class because there were survivors in every class. Or they'll say, because you can survive regardless of what class you're in. But the statistical definition of independence is this line right here. A and B are independent if the probability of A given B is just the probability of A. If knowing that someone's in first class doesn't change the probability that they survived, then being in first class and surviving are independent. If the probability of survived, given that you're in first class, this is my A, this is my B, if that's just the probability of survived, if those two probabilities are equal, then we say A and B are independent. Otherwise, we say that they're not independent. You could also say that they're dependent, but it's more proper to say that they're not independent. And it doesn't matter which of these you put where. If we go to some earlier numbers that we had, if you look at the probability that someone is in first class given that they survived, let me bring that other screen down here. So I'm saying right here, it doesn't matter what order we do that in terms of checking for the independence. If we look at the probability that someone was in first class given that they survived, that's up here. The probability that they were in first class given that they survived is 0.44. But the probability, so that's this right here, but the probability that someone was in first class, we saw that way up here. The probability that someone is in first class is just 22%. So 22% of the passengers were in first class, but 44% of the survivors came from first class. So again, since those probabilities are not equal, then we say the events are not independent. So whether we check these two to see if they're equal, or whether we check these two to see if they're equal, even though we're checking different numbers, we're checking the correct thing or the correct probability statements, and we're getting the same conclusion either way of not independent. Moving on to the topic of joint probability. Related to conditional probability somewhat is a joint probability. In fact, students often get them backwards or interchanged. In both conditional probability and joint probability, you need two events to both happen. But in the conditional probability we talked about before, it was the probability that one thing happened given that the other thing had happened. Now for joint probability, we're just talking about the probability of both events happening. It's usually written with the word and. I like making the word and uppercase. Sometimes the word and is lowercase. Sometimes it's this upside down U that means intersection in set notation. And so it's the probability that both things happen, both events happen. So in terms of our Titanic data, the probability that someone survived and is in first class is 58 out of 795, which is about 7%. And if I go back to this table here, you'll see that of all of the people referred to in this table, this 58 right here are the only ones who are in first class and survived. There's only 58 people that meet that criteria out of the 795 people. So anyways, 58 out of 795 is 730. Unlike the conditional probability, it does not matter what order we write these events in for an and or for a joint probability statement. Just like saying near our college, the intersection of Valley and Temple is the same thing as the intersection of Temple and Valley. Then related to joint is this term disjoint, which is sometimes also referred to as mutually exclusive. When two events are disjoint, that means they can't both happen at the same time. And in that case, the probability that they both happen is 0. So disjoint because they cannot both happen. Furthermore, now this is more along the lines of this term mutually exclusive. Since they cannot both happen, if you know that one of them has happened, then that automatically means the other one hasn't happened because they can't both happen. So knowing that one of them has happened kind of excludes the other one from happening. So the connection between joint probability and conditional probability is this beautiful little formula here for conditional probability. The probability of A given B is the probability of A and B divided by the probability of B. Notice I'm using that upside down U to mean intersection or to take the place of the word and. So back to our Titanic example, if we knew already that the probability of survived and first class is 0.07, and we knew the probability of first class was 0.22, then we can use those two probabilities to figure out this probability. The probability that someone survived, given that they're in first class, this is the A, this is the B, is the probability that they survived and they're in first class, that's the A and the B, divided by the probability that they're in first class, which is the B. So notice what comes after the vertical bar is the event whose probability goes in the denominator. The event that comes after the vertical bar is the event whose probability goes in the denominator. So if you put the probability of survived and first class in the numerator and the probability of first class in the denominator, divide those two, and you get this, which is exactly the same. We go up here. That's exactly the same as the probability we got here for survived given first class. But this survived given first class, that number there came from dividing two numbers in the table. This answer here is exactly the same, except for a little bit of round off error in the 10,000ths place. this probability is exactly the same, and we didn't even see the numbers from the table. We're just dividing two other probabilities. So this is a really powerful way, this formula here, this conditional probability formula, really powerful way to get one probability from two other probabilities that you may know. And since this formula will give me a conditional probability, I can use the results of this formula to check for independence. So here's another example. We were talking about independence earlier. Here's an example of two things that are independent. Suppose we have the following probabilities for a large population of college students. Probability that one of them is male is 60%. Probability that one of them is a smoker, 15%. Probability of male and smoker is 9%. From this and the formula we just used up here, we can calculate the probability that someone is a smoker given that they're male. The probability that someone is a smoker given that they're male is the probability that they're smoker and male, just following this formula right here, divided by the probability that they're male. Again, what comes after the vertical bar is the probability that goes in the denominator. And if you do 0.09 divided by 0.6, you get 0.15. So notice what's interesting about this. We just calculated the conditional probability to be 0.15, the probability that someone is a smoker given that they're male. But in the problem, we were told that the probability someone's a smoker is 15%. So in this case, the probability that someone is a smoker given that they're male is the same as the probability that they're a smoker, which means that in this case, the events smoker and male are independent. Knowing that someone is a male doesn't change the probability that they're a smoker. Okay, now if you take this same formula here and write it as a multiplication problem instead of a division problem, if you can imagine rewriting this algebraically, you get this formula here, or this formula here, depending on which you're calling A and which you're calling B. And this is a formula for finding the probability that A happens and B happens. That's the probability that A happens times the conditional probability that B happens given that A has happened. Or, if you want to know the probability that A happens and B happens, you can do the probability of B the probability of B times the conditional probability that A happens given that B has happened. And you don't have to check both of those. You can do either one of them. It kind of depends what probabilities you've been given in a problem. So for example, in our Titanic data, if you want to know the probability that someone has survived and they're in first class, you can do the probability that they're in first class times the probability that they survived given that they're in first class. So that's 0.22 times 0.33, which is 0.07, which is the same that we got for this probability directly from the table. And also, changing which one I do here, survived and first class could also be written as, let me put this on another line, survived in first class could also be written as the probability of survived times the probability of first class given that someone survived. And in this case, we're multiplying two different probabilities, but we still get a product of 0.07. So this is referred to as the general multiplication rule. It works for any two events, assuming that you know either this conditional probability or this conditional probability, then you can find the joint probability that A and B both happen. Now, to kind of marry together two of the formulas that we've had, earlier we said that A and B are independent if the probability of A given B is just the probability of A. So that means if I can bring down this formula we just had, so notice this general multiplication formula here, if the A and the B are independent, then the probability of B given A, which is this piece right here, the probability of B given A is just the probability of B. So in this multiplication problem, instead of saying the probability of A times the probability of B given A, we can just say the probability of A times the probability of B, because the probability of B is the probability of B given A when the two events are independent. And of course, it doesn't matter what order you do that multiplication in, probability of A times probability of B. So this is very useful when we are told that events are independent, but it's also a useful way to check if two events are independent. So for example, if you want to know if the events survived in first class are independent, then check to see if this multiplication rule, let me put this on its own line, check to see if this multiplication rule has been met. So, is the probability that someone survived and they're in first class, is that and probability the same as the probability that they survived times the probability that they're in first class? If this multiplication works, then they're independent. So, we know this joint probability from before, that's 0.07. The probability of survived we found before, that's 0.16. The probability of survived we found before, that's 0.16. The probability that someone is in first class we found before, that's 0.22. If we multiply those two together, we get 0.03, which is nowhere near 0.07. But even if it was close but not equal to, we would still say this is evidence that they're not independent, because these two probabilities would be equal if they were independent, because this multiplication rule for independent events would work if they were independent. So going back to the college student smoking example, you can do the same kind of check. Is the probability that someone is a male and a smoker, is that the same as, question mark, the probability that they're male times the probability that they're a smoker? So we've been given all of these probabilities in the problem, and when we multiply 0.6 times 0.15, we do in fact get 0.09. So the probability that someone is male and a smoker is simply the product of these two probabilities. And again, I still have it highlighted up here. Whenever that multiplication works, that means the two events are independent. Okay, so let's use a couple of the rules we've learned about to discuss an interesting problem from a game of cards. Suppose we have a standard deck of playing cards which contains 52 cards and 4 of them are aces. And we're going to select 2 cards at random from the deck. And we would like to know the probability that they're both aces. So if we look at this from the standpoint of counting and the very first formula we learned for probability, we need to figure out how many different things can happen if I take 2 cards at random, the number of ways I can get 2 cards, and how many ways are there that I can get 2 aces. And that's actually kind of a simple calculation with combinations, because the number of ways I can get 2 cards is 52, choose 2. Okay, so bring that up on the calculator. Math, probability, combinations, 52, choose 2. So there's 1,300 ways I can get 2 cards, but there's only 4 choose 2. There's only 4 aces, and if I'm choosing 2 of them, there's only 6 ways that can happen. If you're not seeing the 6 ways that can happen, but you're familiar with, what did I just do? Oh, I just did 6 choose 2. I need 4 choose 2. So if you don't believe that there's 6 ways that that can happen, the 6 ways that that can happen are ace of spades with the ace of clubs, ace of spades with the ace of diamonds, ace of spades with the ace of hearts, ace of clubs with the ace of diamonds, ace of clubs with the ace of hearts, and ace of diamonds with the ace of hearts. So there's 1, 2, 3, 4, 5, 6 ways that I could get 2 aces. So anyways, we divide those two. There's 6 ways that I can get 2 aces. There's 1,300 ways I can get 2 cards. So the probability that the 2 cards I get are both aces is 1 out of 221, or about 4.5 out of 1,000. So now let's see if we can get that same probability a different way. Let's rewrite this as a joint probability statement. What's the probability that the first card is an ace and the second card is an ace? So the probability that the first card is an ace and the second card is an ace, using this general multiplication rule here, okay, using that general multiplication rule there, the probability that the first card is an ace and the second card is an ace is the probability that the first card is an ace times the probability that the second card is an ace, given that you know the first card was an ace. Now, the first probability here is pretty straightforward because there's 52 cards in the deck and 4 of them are aces. So the probability that the first card is an ace is 4 out of 52. For the second probability, given that you know the first card is an ace, there's now only 3 aces left in the deck. And if an ace is gone, then there's only 51 cards left in the deck. So this probability is 3 out of 51. And if you multiply the 4 over 52, whether you divide them, whether you simplify the fractions or not, if you multiply the 4 over 52 times the 3 over 51, you get 1 over 221, which is exactly the same as the probability we got up here. So that's just kind of interesting that there's a counting approach to getting that probability, but there's also a using the multiplication rule, the general multiplication rule way of getting that same probability. Okay, then we have a general addition rule, which applies to situations that are referred to as unions, or when we have the word or. The probability that one of 2 events happens, or possibly both of them happen, is referred to as a union. And it's indicated by the word or this big U symbol that means union. And it's called the addition rule because you add together the probability that A happens and the probability that B happens, but then you have to subtract the probability of A and B. So more on that subtraction in a second. But in our example, you want to know the probability that someone's in first class or survived, then that's the probability that they're in first class plus the probability that they survived minus the probability that they're in first class and survived. And we have all those probabilities as decimal numbers from before, so now it's just a little arithmetic problem. Bam, there's the answer. You can also get this directly from the table by looking at all the people in the table who either died or survived. And if you add up everything here that's highlighted in yellow, you'll get 249 passengers out of the 795, which is 31%, exact same number that we got here. What students often mistakenly do is they'll add the 131 from here and the 176 from here, because we had 131 that survived, we had 176 that are in first class, and they will add those 2 numbers together and get 307, and they will mistakenly think that this probability should be 307 over 795. And the problem is, doing it that way, you're counting the 58 people twice, because these 58 that we were talking about before for a different probability, these 58 are part of the 176, but they're also part of the 131. So if you add together the 176 and the 131, you're double counting those 58 people. Hence, the subtraction at the end of this formula. The subtraction at the end of that formula is to get rid of that portion of probability that we counted twice. Another interesting note here is that this formula here, if the two events are disjoint, we talked about this a little bit ago, if the events are disjoint or mutually exclusive, then the probability of A and B is 0. And if the probability of A and B is 0, then this formula here, we don't have to do the subtraction if that subtraction is 0. So that addition formula would just simplify to this. Then we have something that's referred to as complements. This is our last topic for probability. The complement of an event, which can be written, there's notation for it. There's several different notations for it. A with a superscript C, A with an apostrophe that looks like A prime. I've seen it written with the word not A, or with an exclamation mark in front of the A, or with a tilde in front of the A. That's all different notations for a complement. And it refers to all of the possible outcomes that are not in A. So either A happens or it doesn't. And if A doesn't happen, that means the complement has. So therefore, the probability that A happens plus the probability that A complement happens has to be 1. But this is easier. This is most often used as a subtraction problem instead of an addition problem. In other words, if these two things add up to 1, then 1 minus either of these gives you the other one. So if you want to know the probability that A happens, you can do 1 minus the probability that the complement happens. Or if you want to know the probability that the complement happens, you can do 1 minus the probability that A happens. There are many problems, especially a little bit later on in this course, there's many problems where they ask you to find the probability of blah, but it turns out that it's easier to find the probability of blah complement and then subtract from 1. And that's a handy little trick. So that's a bit about it for our chapter on probability.